Well, sorry about the latest video that just stopped while I was writing. I have this 15 minutes restriction, which I think is a great idea, so I really don't want to make longer videos. So, all right, so this is it. We were computing in terms of the g function, what was this equation giving, and all the second order derivatives that are in just one direction were canceling, and we were left with a, let's say, 4 with, sorry, but it's 4 times d2g over du dv. Okay, and well, that should be equal to 0 because that's what the wave equation gives. Okay, so that's it. Our equation now has, I don't know if you already see that, but this is actually simpler than what we had before. Okay, so now we have to solve. Let's get rid of the 4. 4 times something equals to 0. It means that this something is equal to 0. So this is what we have to solve. du dv is equal to 0. Well, of course, this is simpler just because we have one single term instead of the 2 terms we had before. Even though it's still a second order differentiation and it's even a cross differentiation, it's all right. It's not that complicated. So let's do as the small examples we treated earlier. Let's solve that. If d2g du dv is equal to 0, it means that if I kept that order, but I could really solve it in any order you want. That means that the derivative according to u of the derivative according to v of my function is equal to 0. So let's integrate that. Okay, what does that mean? It means that this function does not depend on u. Right, so this must be a function that, let's give that some name, depends only on v. Okay, so I've got now my equation has become that actually dg over dv was equal, and g is again a function of u and v, was equal to only a function of v. Okay, so let's do what comes next. Just integrate that again. We should integrate with respect to v this thing. And so what does that mean? It means that g of uv would actually be a primitive of that function of v. So let's say as this was arbitrary, that would remain an arbitrary function. More about this later on. But I must not forget any constant of integration. It means that I can add anything that depends only on u. So let's give the name L of u. Okay. So that was the analysis part. Okay. And what we found out was that if we had a function that solved this equation, well, let's keep that for the moment in terms of u and v, it had to be one function of v and separately one function of u. Okay, and again, that would be arbitrary functions. Okay, so that was the analysis part. Actually, I'm just doing it on this equation. We saw it was the same as the other one up to some substitution. You can also do the same synthesis that I'm going to perform on the first equation, but it's really equivalent. Okay, so that's the end. Let's say that's the end of the analysis part. And then what would come as the synthesis? Put g of uv is equal to k of v plus L of u, where k and L are arbitrary functions. Okay, then d2 g of uv with respect to the cross derivatives are just going to be equal to, well, you differentiate that according to the L disappears, and you differentiate again that according to U, the K disappears. Okay, right? So that's a solution, and that's it. That's all we need for the synthesis. If we decide that, well, if we put our functions U and V of UV to be the sum of those two separate functions, then it solves the equation. Well, the simplified equation, but you can really, we saw that it was really equivalent to the other equation. And by the way, let's conclude that in terms of F, you could also do some synthesis here. So let's put f of xy is equal to some arbitrary function, let's call that k, of v. V was supposed to be x minus t, and plus L of u, which is supposed to be x plus t. Okay, I don't know, maybe I had the contrary, I don't remember. Ux minus t, vx plus t. Okay, sorry about this. Ux minus t, so I should get according to the notations, but it doesn't matter. Actually, why doesn't it matter? Because these functions are arbitrary. X plus t, x minus t, where k and L solve, sorry, not solve, or any arbitrary functions of class C1. I mean, I need them to be continuous in order to perform some integration. Again, L are some arbitrary constants, functions, arbitrary functions. Okay, and then F solves the one-dimensional being standing for the space dimension. Okay, that's like a string. This is really a string wave equation. And then you're going to ask, but what are the K and L? Why are they arbitrary? If you remember, you already had this kind of arbitrary constant. Well, it was more like constant when you had ordinary differential equations. Well, what changes is that what is a constant for partial differentiation is anything that concerns the other variables. So that's about the same idea. And the interesting thing here is that we've got this the function or functions of these two variables, and it's just that well, we're going to have a look at the Wikipedia page where you have this animation that shows you how this makes two waves that are traveling, one in one direction and the other one in the other direction, actually. Okay, I still wanted to say that you determine K and L because actually you will need some initial conditions and some boundary conditions to find a unique solution of this equation. Very similar to what you saw for the ordinary differential equations, where the arbitrary constants were determined by the initial conditions. Okay, so let's have a look at that on the Wikipedia page. So actually, we've got the same same solving, I guess, that appears here, more or less, I guess. Well, I think it's on the page, general solution, exactly this one. You see, you choose, well, you've got to see if you put some velocity in the equation, you've got to see appearing, and you've got one variable that is going to be x minus ct and another variable that is going to be x plus ct times t, related to the equation where we had, you see, you had some c square, velocity square that comes in front of the second derivative in the space variable. Okay, and well, the animation is a nice one. That one, it shows you that actually this is going to be a sum of, so here we've got something like a string. You see it's the blue one. The blue one is the sum of the green one and the red one. Okay, so the blue one is like a string that is held at its two sides, like the string of a guitar or any instrument. And you do some kind of perturbation, and then the oscillation of this string is actually going to be the sum of two waves. One that is traveling from the right and the other one traveling from the left. You see, the red wave is going from right to left, and the green wave is going from left to right. And here we've got, so that would be your choices, your two separate functions, K and L. Actually, here it happens that these two functions, probably depending on the initial conditions that were given, are going to be the same one, but they apply to one variable which which goes from right to left, and the other one goes from left to right. Okay, and so you get the sum of those two waves, and that's giving you this oscillation of the string, again the blue one. Okay, that's I think a very nice part of a very nice one in differential equations. Okay, thank you very much.